Okay, guys, we will continue. Before ending the previous class, I had asked you a question. Okay, how do you find the total number of leaf nodes available in the binary search tree? Has anyone got the answer for that? You can unmute and go if you have got the answer. Yes, anyone? Yeah, go ahead. I'm not able to hear you.
Ma'am, it will check for 8 elements or not. Okay. If it is null, then we will use it. Ma'am,
Yeah, anyone else? Root order left and root arrow right both are to be null. You're right. Um, okay. So if root arrow left as well as root arrow right both are null, only then I call it as a leaf node. You're right. Okay. Um, can we have something like this? I'll give you two more operations. Okay. Those operations we will take it in the next class, and I'll be discussing for 15 minutes important concept which is called as delete operation. Okay, on the binary search tree. So before I proceed ahead, take down two more questions. One question, voice is breaking. Okay, 1 minute. Yeah, first question, it remains the same. Find the total number of leaf nodes available in the binary search tree. Guys, you can use either recursive function call or iterative function. Both are allowed. Okay. Then the second question, take down the second question. Try it on your own, please. The second question. Write a C function to find the total number of nodes available in the binary search tree. Total number of nodes available in the BST. This is second question. Third, write a C function to find height of the tree. Height of the tree. Okay, whether the questions are clear, please let me know from your end. First one, find total number of leaf nodes. Second, find total number of nodes available including leaf as well as everything. Okay. Third, find the height of the given binary search tree. Three functions you are supposed to write. You can take one full day time, and on Wednesday we will have the discussion done on this. Yes or no? Okay. So I will proceed ahead with a very important discussion that is called as delete operation in the binary search tree. Okay. See, searching has been so easy, so convenient in binary search tree. But when I'm trying to insert, insertion also follows some rules. And when I'm trying to delete, deletion also has certain kind of complications available. Okay. Let me just show you one simple diagram that talks about, okay, now if I want to have a deletion operation done in this particular binary search tree, okay, let's suppose I want to delete an element, say 3, or if I want to delete an element 1, or if I want to delete an element 8. What all are these? What kind of nodes are called these? 1, 3 and 8? Jaldi jaldi comment chahiye. Yeah, they are called as leaf nodes. The case 1 goes like this. If I want to delete a leaf node, you just don't have to bother about it. Just don't have to bother about it. You have to go until you search for that element. Search and delete it is. Okay? Search an element and delete it. You have to go on searching for that element. And when you're going on searching for that element, obviously current will be going ahead and previous will be following the current. I'll repeat again. Whenever you want to have a search and delete operation, you cannot delete simply. Okay, you have to search an element and delete that. When you want to delete an element, a given element, the previous and current will move in the same direction. Like previous always follows current, and current will reach the point of the node which needs to be deleted, and previous will be the parent of the node to be deleted. I think that you will imagine the kind of the code that you have to write. While current arrow info not equal to element, okay, inside that, if or while current not equal to null, anyways you can go ahead. While current not equal to null, if current arrow info is equal to the key to be deleted, at that point you have to break out of the loop. And when you have broken out of the loop, if current is pointing to the leaf node, then what you are supposed to do? If it is the left hand side, if it is the left subtree of the parent, then if it is the left node of the previous, then make the left side of the previous as null and then free the element. I'll repeat again. Previous arrow left is equal to null and then free current. This is how we are doing if I am deleting 3 right now. Okay, now you just imagine like this. I want to delete 4 instead of 3. I want to delete 4 instead of 3. If I want to delete 4, can I directly delete 4 so easily? If I delete 4, what will be the fate of 3? 3 after deletion of 4 will become an independent node, or I call it as an orphan node. Doesn't have parents, though it has, it gets detached with the parents. So before 4 getting deleted, 3 needs to be attached to the parent of 4. 3 needs to be attached to the parent of 4. So it means what? The left hand side of the node to be deleted, the left subtree of the node to be deleted will become the right subtree of 2. Okay, let's suppose I want to delete 2 itself. I want to delete 2 itself. Now there is a complication. Okay, so let us go ahead in this discussion of deletion of a node from a binary search tree. Okay. Case 1 is if the node is leaf node, delete it immediately, don't at all bother about it. If the node to be deleted has one child, the adjustment has to be done in such a manner that the parent of the node to be deleted will become the parent of the child of the node to be deleted. Okay, this I have explained it already. I'll show you with an example. Just pay attention in this. If I want to delete 3, what I will do? I'll make sure 2 gets attached to 3 and 4 is relieved. Okay, this is how the things are taken care if the node to be deleted has one child. If suppose now I want to delete 2, if I want to delete 2, you cannot simply make sure 5 becomes the new root node. You cannot simply push this like this. If you push it like this, what will happen? 5 will become the root node. See, previously what I had done, if I want to delete 4, I will simply attach this to this and delete this. But now that is not the case. I have a subtree. You cannot simply make a 5 or promote 5 as the new root node. You cannot do that. If you do that, what will happen? Let's suppose 5 I have made as a root node, new root node, and I have deleted 2. Then what happens? Instead of 2, 5 would have come here. On the right hand side of 5, there is 3 and 4, which is against the rule of a binary search tree. What is the rule? Elements on the right hand side must be greater than its root. But 3 and 4 both will be lesser than root. Can I do that? I cannot do that. Instead, I use a very important rule. Of applying this. What is that? Whenever you want to delete a node which has both the children, make sure that you are making the new root node which is the in-order successor of the node to be deleted. I'll repeat again. The statement is so crucial. Please listen to it carefully. Whenever a node to be deleted has both the subtrees, that is left as well as right, I cannot delete it so easily. Before deleting it, I will make sure that the in-order successor of that particular node, the node to be deleted, in-order successor of that particular node will become the new root node. It will become the new root node. So in that case, okay, just 1 minute. Okay. Now, in this case, who is the in-order successor? 3 is the in-order successor. I think I have made a mistake. Just 1 minute. Okay, I have made a mistake. This has become 3 and this has to become 2. Okay, you have to have the swapping done between the in-order successor and the node to be deleted. The in-order successor of that particular node is getting swapped, and that will become the new root node of the revised tree. And once you have done that, make sure that you are arranging the things in such a manner that this node becomes free to be deleted. Okay, now suppose I want to delete 6. Okay, you just imagine that this is the overall tree that is available to me. The circled one, only the circled one is the overall tree that is available. Okay, now if I want to delete 3, what should I do for that? Who is the in-order successor of 3? Can you quickly tell me? Successor, who comes after 3 in the in-order traversal? Can you comment quickly? Who is the in-order successor of 3? It is 5. It is 5, not 4. Please, Ananya, you just imagine that this is the circled part is the only tree that is available with me right now for an example. Okay, don't consider the below one. I have considered only the upper one is the BST available for me. With that, the in-order successor of 3 is 5. Okay, it is 5. Now what happens? This 5 would become the new root node. So 5 and 3 are actually swapped. The in-order successor of the node to be deleted, its info part is getting swapped. Actually, it is getting swapped. Then make sure that after swapping, the element where it has reached, it gets deleted. Either it follows case 1 or case 2. What is case 1? After swapping it with the in-order successor, either the node to be deleted will become the leaf node, as in this case right now, or the node to be deleted will become a node with a node with a single child, just like the previous example. I will just restart it again. Okay. So if the node to be deleted, is 2, in this case, first step, you remember it stepwise. First thing is find the in-order successor of the node to be deleted if the node has both the subtrees. Who is the in-order successor? 3 is the in-order successor. Swap the elements. Don't do anything other than that. Once you have found the in-order successor's info part gets swapped with the node to be deleted. Okay, so 3 comes here and 2 comes here. Okay, in this case 2 is right now a node containing single child. Who is a single child? 4 is a single child. So it is case 2. Case 2 talks about deletion of a node with a single child. Apply case 2 for that. What is that? Make sure you are pointing 5 to 4 and then deleting 2. And where 4 will come? Since 2 is on the left hand side of 5, 4 will become the left subtree of 5. This is applying case 2 after swapping with in-order successor. Now, the second example which I had taken, consider only this part of the tree. Leave the lower part, please. Okay. At this point, if I want to delete 3, who is the in-order successor? 5. Swap it with 5. Swap it with 5. Okay. Once I have swapped it with 5, 3 would come here and 5 would go here. At this point, 3 will become a leaf node, which is case 1. That's why invoke either case 1 or case 2. So how do I go ahead in case 1? Simple, previous arrow left, right is equal to null and free of the node to be deleted. Are you getting this explanation or not? Please let me know. You are explaining. The explanation goes in 3 ways. Delete operation will go in 3 ways. First case 1 talks about node to be deleted is a leaf node. It's very simple. Delete that node directly. Second case, node to be deleted has one child. It may have left child or it may have right child. If it has a right child, I'll go backwards. Okay. If it has left child, that left child will become the right of parent. If it has right child, that will become the left of the parent. Okay. Anyhow, the parent of the node to be deleted will become the new parent of its successor. Okay. This is case 2. Case 3 is if node to be deleted has both the children. Then what you are doing? Step 1, find the nodes in order successor. Once you have found out, swap the current node to be deleted with the in order successor value. Node remains intact. Value are getting swapped. Only the values. The value of the node to be deleted will be available in the swapped node now. That swap node, either it can be a leaf node or it can be a node with one child or both the child. Okay, in this case, the node to be deleted will be freed either as a leaf node or as a node containing single child. So either I will apply case 1 or case 2 after swapping it with the in order successor. Are you getting this explanation or you have any doubt with the explanation? Please let me know from your end. If you have any doubts, please ask me again. Okay. Can you please show how the final tree looks? Definitely. Just 1 minute, I will unlock the meet. Okay. See, now what happens? 5, 3, sorry, 1 minute. 1 minute. I'm sorry. Okay. Now in this case, pardon me, this is 2, okay. Now in this case, 2 has come to a position where 2 has a right child. 2 has a right child. Now 4 gets attached to 5. 4 gets attached to 5. It means what? I have 6, I have 3, I have 8, then I have 1, then I have 5, then I have 4. Look at this diagram. This is becoming the new left part of 5, and the one which is shown in the dotted will go off. And when you free this node, its links also will be getting detached automatically. You need not do that. When you call free function, the freeing of the node as well as its related links are being done automatically. Okay, so the final tree will look like this. Okay, Praveen. Now imagine implementation of this function. Imagine the implementation of this function. Guys, I will be giving the program on this step by step on Wednesday. Okay, on Wednesday, I'll be covering this step by step. Please do attend the class on that day without fail. Okay, if you're free tomorrow, we will do it tomorrow itself. I think the CRs have to make sure that if any free class is available tomorrow, let me know. I will complete this by tomorrow itself. Guys, I think I will end the class today because beyond this, I will not tell it right now. I will show you the implementation of this by tomorrow. May I have the CRs? Anushka,
Yes, ma'am.
please let me know. Can I take class tomorrow?
Okay, ma'am.
Yeah, let me know the timing and you can just message me.
Okay, ma'am.
Okay, upload last Saturday's class. I will do that. I'll do that. Okay, so we will end for now. By tomorrow, you should be able to write those 3 functions on your own. And please attend tomorrow's class. That's more important, most important part. Okay, thank you all.
Thank you, ma'am.
Okay.